All right, so we are ready to go, I think. Do you guys have any questions? Okay, good, Aaron. What's your first question? Okay. Okay, so I always have to look these up. So there is a formula for the error bound using all the different rules. So there's one for midpoint rule, one for trapezoidal rule, one for Simpson's rule. So we'll start there. And the Simpson's rule has to do with, here's the formula. The error in Sn, I should have said error in, is less than or equal to, and here's how you can kind of see where Simpson's rule is going to be a bit better than the others. The denominator of this expression is 180 n to the fourth power. And then the numerator is m times b minus a to the fifth power. And m is just a bound on the value of the function. So you can overestimate m if you need to. It's truly the maximum value. Yeah, the maximum value of the fourth derivative of the function. So it's kind of a crazy thing. So m is maximum value of the fourth derivative on the interval a to b. So we just have to get some sort of bound on that and then calculate the rest, because the rest of it we're going to be able to figure out. So let's see, your problem said integral from 3 to 5. So there's our a and b. X to the sixth plus 9x cubed. Did I have that right? Just making sure I interpreted that integral correctly.
To find the error percentage here?
Not a percentage error, I don't think.
What is it?
The problem says to determine an upper bound for the error.
Oh, so what do you have written there? Error?
The error, that's the formula for error using Simpson's rule.
Oh, you just have another two letters after that, so I didn't know what those two letters were.
In. The error in S.
Oh, gotcha. Thank you.
Yeah. Okay, so let's see. And we're looking at, and they said with n equal to 6, right? Yeah, no, Simpson's rule is the fourth derivative, and I think that the trapezoidal rule is the,
second.
Yeah, trapezoidal rule is second. So second for trapezoidal, fourth for Simpson's. And depending on your function, the fourth derivative might be larger, might be smaller. You're just trying to get a bound for it. No problem. Okay, so we've got N, we've got B and A. We just need to bound the fourth derivative. So that means we need to compute the fourth derivative, but that shouldn't be too hard. Here's our function. F of x is x to the sixth plus 9x cubed. The first derivative is 6x to the fifth plus 27x squared. The second is 30x to the fourth plus 54x. The third is 120x cubed plus 54. And the fourth derivative is 360x squared. So I need the maximum value of that expression on the interval 3 to 5. Well, since 5 squared is larger than 3 squared, my m value is going to be 360 times 5 squared, or 360 times 25, whatever that is. Oh, I don't have any batteries in that one. So 360 times 25 is 9,000. Is that right? My calculator's warming up. I think that's 9,000. You guys can check my arithmetic there. Okay, thanks, Erin. So now we've got M, and that means the error using 6 subintervals should be less than or equal to 9,000 times, oops, not 3, undo that, 5 minus 3 to the fifth over 180 times 6 to the fourth power. And so it's just a matter of calculating that. 9,000 times 2 to the fifth divided by 180 times 6 to the fourth. And I get 100 over 81. Now, I don't know what they wanted you to do in terms of rounding. Did they mark it wrong for you, Erin? Okay. So it's sort of a matter of bounding that derivative. And in practice, you might not use the actual value of m, but you might use an approximation for it. Let me give you an example. Let's say we were looking at the function f of x equals e to the x. Every derivative of e to the x is e to the x. And so let's say you were looking at the interval from 0 to 2. Well, e to the x is increasing on 0 to 2. So you would look at the value at 2. So we would want the value of e squared. But since that's not really a very nice number, in order to get a bound on something, we might say, well, e is about 3. So we'll use 3 squared, and that'll be even bigger, which will be okay because we're just overestimating our error a little bit. And so we might say, well, e squared is about 9, or it's about 8. And that would be a good enough approximation for something like this. In this case, they wanted you to use the formula directly, and we were able to get the exact value though. Do you have others, Erin? And are they similar or different? Oh, that was it. Okay, thanks. Any others out there? Yeah, so it's just a matter of, finding those formulas or jotting them down someplace. So you might want to have those handy, but they're not something that you can't look up when you need them. Yeah, that's true, Erin. Um, okay, so coming up next, and I don't have a lot on our schedule for this week. So this is going to be kind of a catch-up week. Get ready for the test. You can ask whatever questions you want. Today, I'll go over a little bit on improper integrals. And then Wednesday, I don't have a specific plan for. Your test will be available next week. You can get started and get ahead on homework for the next area if you want, or you can just sort of catch up on other things. So we'll have kind of a lull in the action this week without a lot of new stuff. So next section is improper integrals, and I'm gonna stop my share. And I'm gonna share, I'm gonna share from, let's see, this will work. There we go. Okay. So hopefully you guys can see the screen. Merrick, I will throw this up in e-learning if I didn't do so already. I don't think I did yet, but I think you can see it, so we should be okay here. So I've sorted out that ability to share from an outside app. So improper integrals they take two forms. The first form is going to be integrals with infinite limits. And then the second form is going to be integrals where the integrand is undefined somewhere on the region of integration. So we're going to take the first type, being those with infinite limits. And so it can be that the upper limit is infinite. It can be that the lower limit is negative infinity, or both. And the way that we're going to define these improper integrals is in terms of limits. So this is where we go all the way back to the very beginning of Calc 1, where we learned about limits and calculating limits. We're going to be using all sorts of limit properties as we go here. So this might be a good time to go back and refresh those if you haven't done so fairly recently. Plus, we're going to use all of this in the next chapter. So the next chapter deals with sequences and series, and we're going to use limits quite a bit here. So this last section on integration is a good segue into our work with sequences and series. Okay, so let's take a look at these definitions. So the first one says the limit, or the integral from a to infinity. So we have some specific value for our lower limit and an infinite value for our upper limit. And what we'll write that as is the limit from a to b, or the limit as b goes to infinity, of the integral from a to b of f of x. In other words, what we're changing is the integral itself, so that that upper limit has what will be a variable, the variable in the limit. In the second case, it's just that the lower limit is negative infinity. So we'll let a approach negative infinity. Notice that in every case, each of the integrals on the right-hand side is one that we already know something about. If we look at the very third case, from negative to positive infinity, we just split it up into two integrals, and then we calculate those separately and make our decisions from there. If we come up with a finite value for our integral, we say that the integral converges to that value. If we come up with an infinite value, we say that the integral diverges. So we're looking at whether an integral converges to some limit, or whether an integral diverges off to positive or negative infinity. So let's see how this might work in practice. And we'll start with one that's kind of nice in terms of the integral itself. We're just integrating 1 over x. Who remembers what the integral of 1 over x is? Thanks.
ln x.
Yep, thanks. Thanks, Caitlin, and thanks, Gabe, ln x. So when we write this, and this is going to be really important so that you can keep track of where you are. The definition of this improper integral says it's the limit of the integral from 1 to b of 1 over x dx as b heads off to infinity. And you guys just told me that that integral is equal to ln of x. Of course, evaluated from 1 to b. And then we're going to take the limit. So essentially, all that's happening here is that we're evaluating an integral just like we have been all semester long and all Calc 1 long. And then we're looking at what happens as that upper limit heads off to infinity. So this is the limit as b goes to infinity, ln b minus ln 1. I can leave those absolute value bars off because b is heading off toward positive infinity, so I don't have any worry about b being negative in this case. The natural log of 1 is 0. What happens to natural log b as b approaches infinity? Does it approach a specific value, or does it also head off to infinity?
It heads off to infinity.
Heads off to infinity. And infinity minus any finite number is still infinite, and we would say that the integral diverges. Essentially, what we're saying, if we want to think about the integral in terms of an area, the function y equals 1 over x, something like that. We'll just put a couple of points on here. And the integral from 1 to infinity represents the area under the curve, that infinite region. And when we say that the integral diverges, what we mean is that we can make that area as large as we want by picking an upper limit as high as we want. So for example, if you wanted to make the limit or the area more than 10, there's a little hint as to what this looks like. Natural log b, so I need the natural log of a number to be at least 10. Well, the number that works there is e to the 10th. So if I went out as far as e to the 10th power, I would have an area under the curve of 10. If I went out to e to the 100th power, I would have an area under the curve of 100. But notice that even though that natural log function grows slowly, it does keep growing. So if I wanted to have an area under the curve of 1 billion, I can do it. I just have to go all the way out to e to the 1 billionth power. And that's what we mean when we say the integral diverges. We can make the value of that integral as large as we want by choosing larger and larger upper limits. Now, sometimes when we're calculating an integral, it's not going to end up diverging. So let's take a look at number 2, because this will show you the other side of this. And also notice that in number 2, we are not looking at a very different graph. However, the graph of y equals 1 over x squared does fall off a little bit more quickly. When x equals 2, y equals 1/4.
This is number 2, right?
This is number 2.
Okay.
So there's my weird graph of y equals 1 over x squared. graphs are very, very similar, but their integrals are very different. So that's what's going to cause a different thing to happen here. So every time we write this up, the limit as b heads off to infinity. And so we're just going to integrate from 1 to b. And I'm going to write that as x to the minus 2.
Got your parenthesis on the number on the first one for the second point you put, just to let you know.
Oh, thank you. We'll put that in there just to make it prettier. Okay. So we want the integral of x to the minus 2, which is what?
And wouldn't that be 2? Sorry, for the first one, wouldn't that be 2, comma 1/2, or no?
It would, absolutely.
Okay.
Oh, and look, I could even fix that without erasing. All right, so we want x to the minus 1 over minus 1, or minus 1 over x. Uh-oh, Bella's upset. I'm guessing some delivery person is here. And we're evaluating from 1 to b. So again, keep in mind, don't lose your limit. Minus 1 over b minus 1 over 1. And what's happening here? So as b gets large, 1 over b heads off to 0. And then this is just a plus 1. And that limit is 1. So in this case, the integral converges to the number 1. Now, what that means is that I can make the area under that curve as close as I want to 1 by choosing a b value, an upper limit, as sufficiently large. So for example, if I wanted to be within 1/10 of 1, I could use b equal to 10, and my area would have been negative 1/10 plus 1, or 9/10. And I would have been within 1/10. If I wanted to be within 1/1,000,000th of 1, I would just have needed to choose b equal to 1,000,000, and I would have had that small enough error. So in this case, we say the integral converges, and we would consider that the area under that curve on the interval from 1 to infinity is equal to 1. So it may look like an infinite region, but it has a finite area, which is a little bit weird. All right, so I'm going to have you guys try one. Yeah, maybe not. No, I think we'll work through this one together too. So this one, you'll notice what I've done is I've changed that x in the denominator to an x to the p power. So if I go back up and look at what I had before, I had p equal to 1, a power of 1 on x. And when p was equal to 1, the integral diverged. Then the second problem, I did p equals 2. And when p was equal to 2, the integral diverged, or converged, sorry. The integral converged to 1. So now what we're going to do is we're going to look at what happens for any old p value. And we already know what happens when p equals 1 and when p equals 2. So we're going to sort of consider most of the other cases. Does that make sense? Remember, p is just a constant, so some number. A lot of times we think p is a positive integer, but it doesn't have to be. It could be a negative number, it could be a fraction, it could be an irrational number, any real number for p. But we do know that when p equals 1, the integral diverges. We showed that back in number 1. So you're going to see why in a minute. We're going to assume that the power is something other than 1. Well, let's write out our definition. This is the limit as b heads off to infinity, integral from 1 to b, x to the minus p dx. Remember, we can bring a power up to the top. And how do we integrate powers? Well, as long as the power is not -1, which it's not because we said p was not equal to 1, we integrate by increasing the power by 1 and dividing by the new power. So this is the limit. B heads off to infinity. Increase the power by 1, x to the minus p plus 1 over minus p plus 1. And then we're going to evaluate from 1 to b. Remember, those values we're plugging in are x values. So we're plugging in b for x.
Why are we plugging in negative p again? I'm sorry.
Well, wait a minute. I didn't plug in negative p. Be careful there. All I did was rewrite 1 over x to the p
Yeah, you're right.
as x to the minus p.
Yeah, okay, I just seen that. Yep.
Okay.
Why'd you? Okay, never mind. I get it.
Now we're going to plug in b for x, b to the minus p plus 1 over minus p plus 1 minus 1 to the minus p plus 1.
So we're doing +1 because we want to keep the p there. Is that right?
No, we're doing plus 1 because we integrated. And when we integrate a power function, we increase the power by 1 and divide by the new power.
Okay.
Right? If you had x, integral x to the 7th, you would say, well, that's x to the 8th divided by 8.
Cool.
And so p is just some unknown power.
All right. Yep.
We don't know what it is, and we're going to consider what happens in a variety of cases right now. So keep in mind, if I raise 1 to any power that is finite, what do I get?
1.
1. That makes that last fraction a little simpler. Limit as b goes to infinity, b to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. Okay, so in terms of b, that last fraction is a constant. There's no b in it, correct? So I'm not really worried about that. That's just some number that depends on what the power was to start with. And the power can be anything except for 1. Notice that if the power were 1, we would be dividing by 0, and this wouldn't make any sense. But we assumed that the power was not 1 because we had taken care of that case with problem number 1. So we just need to look at the first term really closely. And a quick note, remember our power is not equal to 1, which means that p is either less than 1 or p is greater than 1. Those are the only two options because p is not equal to 1. If p is less than 1, then I would claim that negative p plus 1 is a positive number. So let that sink in for a minute. If p is less than 1, then negative p plus 1 will be greater than 0. You're taking something less than 1, you're finding its opposite. Maybe p is 1/2, -1/2 plus 1 is positive. Maybe p is -72. -72 is 72 plus 1 is 73. That's also positive. So for any value of p that's less than 1, -p plus 1 is positive. So in that first term, that means that b to the -p plus 1 is heading off to infinity. Because you're taking a number that's getting huge, remember b is getting large, and you're raising it to a positive power. So it just keeps getting larger and larger and larger. So the integral, since it's heading off to infinity, the integral diverges for any power less than 1. On the other hand, if p is greater than 1, -p plus 1 is less than 0. -2 plus 1, less than 0. -75 plus 1, less than 0. Since b is now being raised to a negative power, as b gets larger, the fractions in that first term actually get smaller and smaller and smaller. And b to the -p plus 1 heads off to 0. And that means that the integral converges to what we have in the second term, to -1 over -p plus 1, which is kind of ugly looking. So I'm going to multiply by -1 over -1 and get 1 over p minus 1. So what does this mean in practice? Well, pick a number, pick a power for p, something other than 1 or 2 that we didn't do already. Gabe, pick a number for me. It can be a whole number, it can be a fraction, whatever you want.
2.
No, don't do 2. We already did 2. We did 1 over x squared. So pick something other than 2.
9.
9. Okay. So for p equal to 9.
5 trillion, actually.
All right, we'll do 5 trillion later. Right now, we'll do 9, because 5 trillion just takes too much space for me to write all those zeros. I have to move myself off into scientific notation. All right, if the power were 9, then the problem would have been this one, 1 over x to the 9th dx. We're saying that this integral converges. You picked a number that was bigger than 1 to 1 over 9 minus 1, or 1/8. And we could do the exact same work that we did in problem number 2 with the power of 2, just using the power of 9, and we would find that the integral converged to 1/8. If, on the other hand, you had chosen p equals 1/2, little note here, 9 is greater than 1, that's why that integral converges. 1/2 is less than 1, and the integral from 1 to infinity of 1 over x to the 1/2, which by the way is the same as the integral of 1 over the square root of x, diverges. So based on that power alone, you can tell whether the integral converges or diverges for this specific function family, right? We were working with a very specific function family 1 over x to a power. Okay, so Aaron E., if P were 5,000, the integral would converge to
5 trillion?
1 or 5 trillion would the integral would converge to 1 over 5 trillion minus 1. 4,999,999,999,999.
I'm more of a visual person, so could you write that out?
No, you can write it out for yourself. You'll be able to just think about it. It doesn't matter what the number is. If your power is greater than 1, the integral is going to converge to 1 over that number minus 1. All right, so we're going to do one more of these, and this is one in the scenario where we're looking at, I kind of switched colors here accidentally, but that's okay because we'll be able to see the difference. To one where both limits are infinite and how we have to handle this. So in order to handle the scenario where both limits are infinite, what we're going to do is we're going to split this into 2 integrals. The first one is going to have lower limit negative infinity, and our function is going to remain the same. And the second one is going to have upper limit of infinity, function remains the same. And we can pick any real number between negative and positive infinity to split this apart at. But we want to be clever so that we make our work as simple as possible. So what number should I pick between negative and positive infinity? Any number you want, but try to make things as simple as possible.
1.
Simpler than 1.
0.
0. Yeah, 0 will be a little bit simpler, and we'll see that when we do the calculation. Does that mean we couldn't do it at 1? No, we absolutely could, but our calculations will be much easier. And notice that this function, since the only power of x in it down there in the denominator is an even function, is an even power, we have an even function. It's symmetric about the y-axis. So we'll get some nice stuff from that as well. All right, so let's see if we can calculate each of these. We're going to calculate them separately and then add them together. Unless one of them turns out to diverge, in which case we'll just say, okay, the whole thing diverges. So I'm going to start with the one that we didn't do any like yet. So integral from negative infinity to 0, 1 over 1 plus x squared. Remember, this is a limit. And I use a here because we're used to using a for our lower limit. A heads off to negative infinity. Integral from a to 0, 1 over 1 plus x squared. So I have to remember, what is the integral of 1 over 1 plus x squared? This was in our
2 ln x of 1 plus x squared.
Nope.
Sorry, 1/2. Sorry, 1/2.
Nope. If this were going to be an ln x, I would need to let u equal 1 plus x squared, and then I would need a du of 2x dx, and I don't have an x hanging about here. The antiderivative is not a natural log, it's some other function.
Oh yeah, isn't it tangent maybe? Yeah.
We're getting warm, not tangent.
Inverse?
Inverse tangent. Oops, negative infinity. All right, tangent inverse x from a to 0. So I need the limit as a heads off to negative infinity. tangent inverse 0 minus tangent inverse A. All right, tangent inverse 0 is 0. It's kind of nice. And now I need the limit of the inverse tangent function. By the way, you could do this in Mathematica. You could do this on your Inspires or your TI-89s. This is looking at, remember the tangent function had vertical asymptotes at multiples of pi over 2. So the inverse tangent function flips that and has horizontal asymptotes at pi over 2, negative pi over 2, and just slants sideways. So it's like that tangent function laying on its side. And the limit as A heads off to negative infinity is that horizontal asymptote, or negative pi over 2. So 0 minus negative pi over 2 is positive pi over 2. And that's the integral from negative infinity to 0. Any guesses on the value for the integral from 0 to infinity?
Negative pi halves.
Nope. Here's the original function.
Pi halves.
Pi halves. Yeah, notice that this function is symmetric about the y-axis, and that red area and that green area are going to be the same. If you do the work on this and write out your limit, we should come up with that. This time b heads off to infinity. The integral is still equal to the tangent inverse. So we've got the limit as b goes to infinity, tangent inverse b minus tangent inverse 0. That's still 0. And that's heading off to pi over 2. So the first integral converged to pi over 2. The second integral converged to pi over 2. Our original big integral that went from negative to positive infinity converges to pi over 2 plus pi over 2 or pi. So lots of work there.
Could you go back down for 1 second, please?
Absolutely.
Thank you.
So the scenario on these problems was dealing with one or both limits of integration being infinite. And that caused the problem of needing to deal with this in terms of a limit, as that value either went off to positive infinity or off to negative infinity. So the other scenario is when you have discount. Did you want me to go back?
Yeah, I just have to write down like the last like two words.
You good?
Yep, we're good.
Okay. So the
Yeah.
other scenario deals with discontinuities in the integrand. So someplace where the expression itself is undefined. If you take a look at number 1, notice that 1 over x is discontinuous at x equals 0. Same for number 2, discontinuous at x equals 0. If we look at number 3, I'll scroll us down. Oh, there's that 1 over x to the p again. That's sort of popping up. Seems like it must be kind of important. Also discontinuous at x equals 0. If you look at number 4, where is that function discontinuous? At x equals, where's the problem spot? Where is the function x over 9, square root of 9 minus x squared? Where is it undefined? Other than places where the stuff underneath the square root is negative. Where else do you have a problem spot? At 3, thanks Caitlin. Yes, 9 minus 3 squared is 9 minus 9, so that gives us a 0 in the denominator. And since 3 is in our interval of integration, we're going to have to compensate for that in terms of a limit. If we look at number 5, number 5 has a problem spot right smack in the middle. So we're going to have to split that up into 2 pieces because we can't have our problem location being in the center of our limits of integration. So we're going to have to split that at 1 and look at 2 separate integrals. All right, so we'll look at that last. Notice that these first 2 look very familiar. They look like the first 2 problems we did, but I've changed the limits of integration. So we don't have an infinite limit of integration now. We just have 0 to 1. All right, so let's see if we can do this. Let's try number 1. We already know the integral is ln x. And we also can look at this. Notice that we are switching out the problem spot, the k. So we switched our b to some value k. And we're saying, let's let k approach b from the left. That's really important if we think about it. It has to be from the left because our whole region of integration from A to B is between A and B. So we're always going to approach B from the left. Similarly, if we're approaching A, we're going to approach A from the right. And so you'll see that in the second one. If we're discontinuous at both places, at both A and B, then we have to split it up and we use something in between again. And if we're discontinuous somewhere in the middle, we split it up wherever we're discontinuous. So we've got really 4 different possibilities here. I think I have an example of number 1, number 2, and number 4. Number 3 comes up very rarely. All right, so let's see how we would write this up. 0 is the problem spot. So I'm going to say, let's let k approach 0 from the right. Remember, our whole region goes from 0 to 1. So I have to approach 0 from the right. And I want the integral from k to 1 of 1 over x. And again, I tried to keep these integrals relatively straightforward for calculating. All my values are larger than 0, so I can get away without having the absolute value from k to 1. And
is that positive k up in the integral for the first discontinuous point up top?
I'm sorry, say that again.
Is that a positive k in the upper limit? first.
right here, this right here?
No. At the very top, it says this.
Oh, okay. Let me get
I
rid of it.
can't tell because you have a circle there.
Oh, that was just a K. I wouldn't,
Okay.
the
I
only
just wanted to
place,
hear.
the place that there is a plus sign and a minus sign is after them. So I did say as K approaches B from the left, because you
So
would
this would be
have
a
to
plus
approach
sign.
B from the left-hand side. So there is
Oh,
a minus sign, and I will share this document with you, so then you'll be able to zoom in on it however you would like to and see all that.
there's only a minus sign after the B though, right?
That's correct. And also there's a plus sign after the A from the
Okay,
left
thank
and
you.
from the right. All right, so I want ln, oops, K is still approaching 0 from the right, and I want ln1 minus ln K. ln1 is 0. All right, what happens to the natural log function as we approach 0?
I'm sorry, where's that plus sign after the A? I can't seem to see it. You have it covered up?
No, I do not. It's in this one. Are you looking here?
Oh no, I was looking at the one above that. Okay, I see now. Thank you.
So here's my natural log function. As I approach 0 from the right, what happens to my y values? As I approach 0 from the right, what happens to my y
Decrease.
values? What do they approach? Decrease is not specific enough.
They approach negative infinity.
Very good, thank you. They approach negative infinity. So 0 minus negative infinity is infinity, and we would say the integral diverges. Okay, so you guys try number 2. So same setup. See if you can come up with whether or not the integral converges or diverges. And if the integral converges, I need a number, like the integral converges to 72 or something like that. I'm going to pause this for a minute. Okay, what did you guys come up with? So let's do a quick 3, 2, 1, go, and let's type in the chat either converges or diverges. All right, go. I didn't say 3, 2, 1, but you could go anyway. Converges or diverges? Looks like everyone's deferring. All right, well, we're gonna set this one up the same way we did the other one, Gabe, so we should be able to do that. These start to look very much the same as we move from problem to problem. I agree with Aaron and Merrick that the integral diverges. So let's see how we came up with that. So we're looking at a limit. Again, K approaches 0 from the right. The only thing that changed from this problem to the last one is the 1 over x became a 1 over x squared. So integral from K to 1, 1 over x squared, which I'm going to think of as x to the minus 2. And then I'm going to integrate that. And I get x to the -1 over -1, or -1 over x, from k to 1. This is the same function we integrated on the previous set of problems, number 2. So this is the limit as k approaches 0 from the right. -1 over 1 minus -1 over k. This first term is just a -1. We've got a minus, so that's a plus. But this thing's heading off to infinity. Subtracting 1 from something that's getting huge, it's still getting huge. That limit is infinite. And the integral still diverges. So any ideas on numbers that you could use for the power on that integral that would have caused the integral to converge? We now have 2 examples, p equals 1 and p equals 2, where the integral diverged. Any ideas on powers that would cause this integral from 0 to 1 this time instead of from 1 to infinity?
Odd numbers?
I'm sorry?
Odd numbers?
Nope, 1 is odd. Remember, you used 1 back here. 1 is definitely odd, so odd numbers isn't the trick. Positive powers. Be more specific, Aaron C. What kind of positive powers?
Other than 1?
Gabe, say that again.
Other the positive powers other than 1?
Okay, well, we just used 2, and with 2, the integral diverged. So all positive powers definitely.
Odd powers other than 1?
Nope. Oh, okay. So, all right, I get where Aaron C is going with this. Yes, Aaron, but then it would actually be a p-value that was negative, because if you had, I see where you're going with this. If you had integral as an example, remember our form is 1 over x to a power. So if that power itself had been the negative something power, I'll do -3, then we would actually have something, we would have x to the +3, and I think that's what you meant by positive power, Aaron C. And then there's no problem because we don't even have a denominator anymore. So that's true. So clearly, if p is negative, if p is less than 0, integral 0 to 1, 1 over x to the p dx is going to converge, because that negative power in the denominator becomes a positive power in the numerator. All right, but there's more. There are more powers that will cause this to converge. Remember that fractions are numbers too. So for example, let's try this one. Let's try integral from 0 to 1, 1 over the square root of x. That would be integral of 1 over x to the 1/2 power. So this would be the case where p equals 1/2. And if we try this, remember it's still a limit. We're letting that lower value head toward 0. And 1 over x to the 1/2 is x to the -1/2. we do our integration, we've got x to the 1/2 divided by 1/2, or times 2, from k to 1. Two times 1 to the 1/2 minus 2 times k to the 1/2. But k is heading towards 0 now, and 0 to the 1/2 is just 0. And that's just 2. This limit is 2. And the integral converges to 2. So the next problem is actually that same integral 1 over x to the p. But we're going to consider what happens for various choices of p. We already know, just like before, that the integral is going to diverge for p values equal to 1. So let's assume that p is not equal to 1. What that allows us to do is use the power rule, because remember, when p equals 1, that's when we get the natural log for our integral. So this allows us to use the power rule. We want the limit. K approaches 0 from the right again. Integral k to 1 x to the minus p dx. Very careful with our notation. X to the minus p plus 1 over negative p plus 1 for our integral. Evaluated from k to 1. Plug in 1. 1 to any constant power is just 1. So I get 1 over minus p plus 1 minus k to the minus p plus 1 over minus p plus 1. And again, we're going to think about what happens to that last term. If p is less than 1, then negative p plus 1 is positive, and k to the minus p plus 1 is going to head off to 0. And in this case, the integral converges, because that second term heads off to 0, to 1 over negative p plus 1, or 1 over 1 minus p. That's only if p is less than 1. And in the scenario where p is greater than 1, negative p plus 1 is less than 0. And now you have this thing headed to 0 in the numerator, but it's raised to a negative power. So it's actually headed to 0 in the denominator. And k to the minus p plus 1 is heading off to infinity. Denominator heading to 0 means fraction heading off to infinity. And the integral diverges. So what we can pull together from this number 3 and the very first number 3 that we did is this. I'm going to actually jump to this next page. If we have integral 1 to infinity, 1 over x to the p dx is going to diverge if p is less than or equal to 1 and converges to 1 over p minus 1 if p is greater than 1. And then the second one, the integral of 1 over x to the p dx from 0 to 1 diverges if p is greater than or equal to 1 and converges to 1 over 1 minus p if p is less than 1. So that puts together those two number threes, which actually are going to come in extremely handy and be extremely useful. We're going to need this again in the next chapter and beyond. So these are going to lead us to something we call a P series. So right now we're talking about integrals. Later we'll be dealing with expressions like this that show up in a series or a sum. So
Is that if p is less than or equal to 1 at the very, very top?
At the very, very top, absolutely.
All right, thank you.
Yep. So I am going to sneak myself back to one of those other problems. Remember, you can always listen back if you need to. Okay, so we're going to jump ourselves back to these. How about number 3 or number 4 rather? We already did number 3. Okay. So we said the problem here was at 3. So this time it's at the upper limit. So I'm going to just draw my number line to keep track of this. We're going from -1 to 3, and we're going to have to approach 3 from the left. So when I set this up, it's going to be the limit as k approaches 3 from the left, integral -1 to k x over square root 9 minus x squared dx. So this problem is a good problem in practice for integration because you need to think about what method of integration you would use for that integral. My hint is that this is a problem you could have gotten back in Calc 1. So you don't really need a bunch of fancy methods of integration. You can do this by one of the methods that you came up with back in Calc 1 and that we reviewed right at the beginning of the semester here. So I'm going to pause this again, and I'm going to ask you to go ahead and compute that integral and then evaluate from -1 to k and then take the limit. So notice that this ends up being a straight substitution problem. Nothing super fancy there in this integration. And so we're going to integrate u to the -1/2. So we'll increase our power by 1 and divide by the new power, but dividing by 1/2 is the same as multiplying by 2. So my 2's end up canceling there, and I end up with a minus square root of u. Which, remember, we were working with x's, so I'm going to go back to my original limit. K goes to negative. K approaches 3 from the left. Our integral is negative square root of u, so negative square root of 9 minus x squared. evaluated from -1 to k. And I'm going to plug in my k minus square root of 9 minus k squared minus square root 9 minus -1 squared. Oops, hit my down arrow there. I can't close that parenthesis because I'm just off too far to the side of my page. But I think we're pretty good here because notice that as k approaches 3 from the left, that first term heads to 0. And that second term, we've got a minus minus, so it's plus square root of 9 minus 1. -1 squared is +1. And so that's the square root of 8. Since we got a finite answer, the integral converges to square root 8, or if you like to simplify square roots, to root 2. So nothing too bad there. Any questions on that one? Okay, let's do the setup on number 5, and then you guys can try it. We'll do the setup together. So 5 is a problem where the trouble spot is in the middle. It's at x equals 1. So we're going to split this into 2 integrals. Integral from 0 to 1. And I'm going to write x minus 1 to the -2/3. Plus integral from 1 to 2, x minus 1 to the -2/3. And then for each of those, we're going to write them as a limit. So for example, the first one is going to be limit k approaches 1 from the left, integral 0 to k, x minus 1 to the -2/3. And the second one is going to be pretty much the same, but k approaches 1 from the right. And the k is at the bottom limit, x minus 1 to the -2/3 dx. So go ahead and try to evaluate those two limits, add them together. Remember, if one of them turns out to be infinite, then the whole thing diverges and you don't have to keep going. But if both of them are finite, then you'll add them together to find the value of the integral. I just noticed I have a typo, a draw O. I don't know what it's called when you're not typing and you write the wrong letter. So this should have been not from k to 1, but from k to 2, because my upper limit is 2, not 1. So as you're doing number 5, make sure you change that second upper limit to a 2. So half the battle on this one is going to be plugging things in and noting signs correctly. Notice that this first term, as k approaches 1, that's going to head to 0. And then my second term is going to be -3 times -1. -1 to the 1/3 power, the cube root of -1 is -1. So my first integral is equal to 3. And my second integral, I think, should also be equal to 3, but let's check it out. This is the limit. K approaches 1 from the right this time. 3 times x minus 1 to the 1/3 from k to 2. Plug in my 2 and my k, and let k approach 1 from the right. That's a 1, so 3 times 1 is 3. That's heading to 0. That limit is also 3. And since both integrals converge, no e on that, both integrals converge, the original integral converges to 3 plus 3 or 6. And if you wanted to think about, I'm gonna actually stop my share.
And how do we know they're converging again?
I'm sorry, say that again.
And how do we know they're converging again?
Well, because the value of the integral was a finite number and not infinite. Remember, converging means that we can make that, thinking of it as area under a curve, although it might be a net area, we can make that as close to a finite value as possible by taking our limit as close as we can get, in this case, to 1. Because 1 was the problem spot. So had we come up with infinity or negative infinity as the value of our limit, we would say that the integral diverges. Since we came up with a finite number for each of those, the first integral converged to 3, the second integral converged to 3, the sum of those integrals converges to 3 plus 3 or 6. I'm going to stop my share there for a minute. I want to share a couple of things. So I'm going to go, let's actually open this first. So just a quick note, you can do this in Mathematica. So if you want to integrate something, and I'm not going to necessarily, although we could do that last one, what was it? It was 1 over x minus 1 to the 2/3 power. And x ranged from 0 to 2. And it's sort of interesting how they gave us the answer 3 minus 3 times -1 to the 1/3 power. But if I say numerical value, seems to be doing something strange with complex numbers. So I am going to say real part. Why are we getting 1.5? Let's go back here and say real part. Really? So it doesn't like that. Let's see what happens if I split this up. So we needed to split 0 to 1. And I'm going to kill all of these oddball things. So there's the integral from 0 to 1. And I'm going to just say numerical value. Not understanding why this is giving me this as though it's a complex number. What's the problem here? So let's try it this way. 0.99. So this really doesn't like the x minus 1 to the 2/3 power. Let's try this. Wow, we stumped Mathematica. I am going to have to ask my colleagues on what's going on there with integrating improper integrals. So something strange is happening there. I think that you'll end up okay on the Inspires and the TI-89. So let me grab my Inspire. It's sitting right here and see if it has the same troubles. I don't think it will. So integrate, we were going 0 to 2, and it was 1 over x minus 1. Is that right? X minus 1 to the 2/3 power. To the 2 divided by 3 power. I think that's right. Oh, real valued root. Thank you, Aaron C. So I think there's probably a real valued integrate function in Mathematica that I should have used to get the correct answer in Mathematica as well. Or I could have used the Wolfram Alpha entry and said real valued. Thank you. And yes, the calculator does give 6 without any issues. The Inspire does, which would mean that the TI-89 should as well. Oh, Merrick, I think in Mathematica it's not going to care because it's still going to see that as it's looking at it as a complex valued function. So it's looking at imaginary solutions to things. And that's what it's giving us is the imaginary valued solution. Okay, thanks, Aaron. Okay, so is the real, I'm not sure what you mean, Merrick. Let me go off and peek at it in Wolfram Alpha. So the real valued root that they're talking about there is the normal cube root of x, or cube root of x minus 1 in this case, the way we think of it in what you get when you come up with the real number. The principal root, to me, should also be the same thing, but Wolfram looks at things a little bit more globally. So when they use the principal root, they're talking about one of the complex roots of a number. So for example, x equals 1 has 3 cube roots. One of them is the real root, which is 1, and the other 2 are imaginary roots. And somehow that's what it's giving as the solution to that problem. I noticed that at least on my computer, the standard computation time is exceeded. So it's actually not even computing that in Wolfram Alpha for me unless I do use the real valued root. I'm not sure what you mean by in the keyboard, Merrick. Yeah, yeah. Let me ask the other math colleagues what you would do here in Mathematica to get the real valued integral that we want. Oh, okay, gotcha, Aaron C. Thank you. Are Merrick, are you looking at the keyboard on on a phone in the app or on the website? Okay. Because I'm not seeing that. My computer wouldn't even do it. It timed out on me. It wouldn't even give me the 6 when I went to real valued root. So I'll sort this out and figure out how you can integrate that. I'm guessing maybe there's something called, I don't know if this is going to be legit or not. If real, at least it didn't yell at me. So in Mathematica, when I did this by nesting that inside real, R-E-A-L, it gave me the parts individually. I want to see if it works if I go from 0 to 2. Yeah, it's just if we had not messed with it. So let me go back. I'm going to reshare. After I delete all this other stuff I tried. Okay, so there I am resharing that integral, and we're going to go ahead and compute it again. If we had just done that and not tried to simplify it, we would have actually been okay. Because at that point in time, if we just go ahead and simplify, we get 3 minus 3 times -1, which is 3 plus 3, which is 6. So had we done that, we would have been okay. Trying to get them to do it for us is really where the problem is. So this step is really not a problem. The problem is with that root of -1, because they're looking at it as the cube root of -1 being the imaginary root of -1 as opposed to -1 itself. Thanks, Aaron C. And that's exactly what I did. I said, I clicked the prompt for real valued root, but it's still timed out on mine. So Mathematica doesn't have any problem with it other than the simplifying piece. I don't know what that will do now. See, that's where it's giving me the wrong root. So root reduce is not the one we want. Okay, good. All right, so I think we're probably good for today. I'm going to kill this share. I'm still going to try to figure out why that won't work for us in Mathematica and give us the simplified version. So okay, so any last minute questions? All right, I am going to end us for today then. And I will see you guys all on Wednesday. So make sure you bring your questions Wednesday, because it's really going to be just question review day. If you want to hang out and work on homework, you could do that too, and then just do questions as they pop up. Or if you've done a lot of them already, that's probably more useful for how we spend our time, because then you can ask me questions while I'm there. Okay? All right, I will see everyone Wednesday.
All right, thank you. Have a good rest of your week until Wednesday, guys.
Yep, you too. Bye-bye.
Bye-bye.